Le Chatelier principle. When we talk about an equilibrium reaction, the factors which influence this type of reactions are: first one is temperature, then pressure, concentration, etc. The equilibrium condition depends these three factors in a large extent. So what happens when these factors changes? And Le Chatelier principle explains about this. So according to Le Chatelier principle, if we change any one of the factors which influence the equilibrium, so if we change temperature, pressure, and concentration in a system at equilibrium, the system will tend to adjust itself in such a manner to undo the effect of the change. If we change temperature, pressure, concentration in a system at equilibrium, the system will tend to adjust itself in such a manner to undo the effect of the change. So now we have to know how the system adjusts itself when any one of these factors changes in equilibrium state. Let us discuss about the temperature change. How the change in temperature affect the equilibrium. So first of all, we have to know whether the reaction is exothermic or endothermic. So consider this is an equilibrium reaction. Here, if forward reaction is endothermic, then surely the backward reaction will be exothermic. If temperature increases, the rate of endothermic reaction increases. That means the equilibrium shift towards the direction of endothermic reaction. If, for example, if temperature increases, for this equilibrium reaction, the equilibrium shift towards right. That is, the equilibrium shift towards the direction of the endothermic reaction, that is A to B, and the backward reaction rate decreases. Similarly, the decreasing temperature favors the backward reaction. That means B to A conversion will occur in a faster rate. For example, if we talk about the effect of temperature in Haber process, the equilibrium reaction is N2 plus 3H2 reversibly gives 2NH3. And the delta H value of this reaction is minus 93.74 joules. So the minus sign represents the forward reaction is an exothermic reaction and the backward reaction is endothermic reaction. So since the forward reaction is an exothermic reaction, increasing temperature reduce the rate of forward reaction. So normally when temperature increases, the equilibrium shift backwards. That is, the decomposition of NH3 occur in a faster rate when temperature increases. So the Haber process should be done in a lower temperature. Then only we can prepare larger amount of ammonia. But one more thing is there, that is, if the temperature is very low, the kinetic energy of these gas molecules will be less. Because of that, this reaction will not occur very easily. So the optimum temperature for Haber process is 773 Kelvin. Same way, if we talk about the decomposition of PCl5, decomposition is like this. PCl5 reversibly gives PCl3 plus Cl2. And this is an endothermic reaction. That is, the decomposition is an endothermic reaction. And the delta H value for this reaction is delta H equal to 92.5 kilojoule. So here, when temperature increases, the extent of endothermic reaction increases. That is, the decomposition increases. So increasing temperature favors the decomposition of phosphorus pentachloride. Then the next factor is pressure. In an equilibrium reaction, pressure influence only when the reacting species or the product formed are gases. So the change in pressure is not applicable for liquid and solid systems. And the increasing pressure favors the direction of the reaction in which, so increasing pressure favors the direction in which number of moles is less. Number of moles is less. Or we can say increasing pressure favors the direction in which pressure reduced. For example, in the case of Haber process, the reaction is N2 plus 3H2 reversibly gives 2NH3. Here, the number of moles in reactant side is here 1 plus 3, that is number of moles in reactant side is 4, and in the case of product side it is 2. So, when pressure increases, the equilibrium shift towards the direction in which number of moles is less. That is, equilibrium shift from reactant side to product side. So, increasing pressure favors formation of NH3. On the other hand, in the decomposition of PCl5, PCl3 plus Cl2, here number of moles in reactant side is 1 and number of products is equal to 2, 1 plus 1. So, when pressure increases, the reaction shift in the direction where the number of moles is less. So, rate of backward reaction increases with the increasing pressure. So the increase in pressure is not favorable for the decomposition of PCl5. The third one is concentration. So let the reaction R reversibly gives product P. So if concentration of any one of the substance increases, then the equilibrium will shift in the direction in which the added substance is used up. For example, if the concentration of reactant increases, then the equilibrium reaction shift towards right. That is reactant to product. This favored reaction is the favored one. Forward reaction will occur in a faster rate. On the other hand, if the concentration of product increases, then equilibrium shift backwards. So equilibrium shift backwards. For example, in Haber process, N2 plus 3H2 reversibly gives 2NH3. So in Haber process, the required product is ammonia. So if you want to prepare ammonia in larger amount, we need to remove ammonia in regular intervals of time. Then only we will get ammonia in a larger quantity. Otherwise, formed product will convert it back into the reactant. Or we can increase the amount of ammonia by increasing the amount of reactants. That is by increasing the concentration of nitrogen and hydrogen used in this reaction. While in the case of decomposition of PCl5, by increasing the amount of PCl5, we can easily decompose PCl5. The last one is effect of addition of inert gas. Effect of addition of inert gas. Addition of inert gas is significant only when there is a change in volume. So significant only when there is a change in volume. That is, at constant volume, the inert gas will not affect the equilibrium. For example, R giving P. So at constant volume, if we add inert gas into this reaction, there is no change in the concentration of reactant and product. That is, the ratio of their moles to the volume, remains same. So if we add inert gas into an equilibrium reaction at constant volume, the concentration of the reactant and the product will not change. That is, their moles to the volume remain same. So there is no significant change in the equilibrium reaction. So next we have to check what happens when volume changes. So we are going to check what happens at a constant pressure. So at constant pressure, that is the reactant reversibly gives product. So when we add inert gas to the equilibrium reaction, volume of the reaction mixture increases. So naturally, the number of moles per unit volume of the reactants and product decreases. And hence the equilibrium shift in the direction in which there is increasing number of moles of gases. So the equilibrium shift in the direction in which increasing number of moles of gases. So the equilibrium shift in the direction in which increasing number of moles of gases. For example, in the case of formation of ammonia, at constant pressure, the addition of inert gas shifts the reaction backwards. That is what we told earlier, that is the reaction shift towards the direction in which increasing number of moles of gases. That is, here number of moles of gases is 4 and here it is 2. So direction in which increases number of moles of gases means from right to left. So equilibrium shift backwards. So from these, it is clear that the addition of inert gas is not significant when change in number of moles delta n equal to 0. So addition of inert gas cannot change the equilibrium when delta n equal to 0. We know the equilibrium constant in terms of pressure Kp equal to constant Kx into P raised to delta n. So when delta n equal to 0, Kp becomes Kx into P raised to 0. That is Kp equal to Kx. That is, the equilibrium is independent of the pressure term. Up to this, we were talking about the chemical equilibria and the Le Chatelier principle. Now we are going to talk about physical equilibria and the Le Chatelier principle. That is the effect of temperature, pressure and concentration in vapor pressure, boiling point, freezing point, solubility, etc. So let us take the equilibrium of evaporation and condensation, that is conversion of liquid state into, that is the equilibrium between liquid and the gas. Here in this equilibrium, when temperature increases, as we already told, increasing temperature favors the endothermic reaction. So here in this physical equilibrium, liquid to gaseous conversion is an endothermic process and the backward conversion is exothermic. So when temperature increases, liquid converts to gaseous state or the reaction shift from left to right. So forward reaction increases in a larger extent. So the increasing temperature favors evaporation. Along with increasing number of gaseous molecules, vapor pressure also increase. So vapor pressure of the system increases. That is, vapor pressure of the reaction mixture increases along with the increase in temperature. But when we increase pressure, that is, if pressure increases, the conversion occurs in reverse direction. That is, when pressure increases, more gaseous molecule converted back into liquid state. That is, the backward reaction is the favored one. That is, vapor state to liquid state conversion occurs in a faster rate. So if we talk about the boiling point of this substance, so here more number of molecules are exist in liquid state. So we have to increase the temperature of the system to attain boiling point. So that indicate boiling point increases with the increasing pressure. So boiling point increases with the increase of pressure. Similarly, if we talk about the equilibrium between solidification and fusion, the solid reversibly gives liquid. So if you talk about the effect of temperature and pressure on melting point, it varies with the substance. For example, if we talk about the melting of ice, that is ice to water. In the case of ice, melting causes decrease of pressure. So melting of ice causes decrease of volume. So that means when we increase the pressure, the equilibrium shift towards right. So when we increase pressure, equilibrium shift to right. That means the increase in pressure lowers the melting point. The increase of pressure lowers melting point. So if we want to retain the equilibrium, we have to lower the temperature of this system. Then if we talk about the case of sulfur, that is sulfur solid to sulfur liquid, melting causes increasing volume. Thus decrease the pressure So the conversion is from right to left, that is liquid sulfur to solid sulfur. So that means the increase of pressure increase the melting point of sulfur. So increase of pressure increase the melting point of sulfur. So that means if we want to retain the equilibrium, we have to raise the temperature of the system. Then the last one is effect of temperature on solubility. There are some substances in which dissolution is endothermic, while the dissolution of some substances are endothermic. So the dissolution may be endothermic or exothermic. So the temperature dependence is based on this endothermic and exothermic behavior of the dissolution process. If the dissolution is endothermic, then the increasing temperature favors the dissolution process. So solubility increases with the increases with the increase in temperature. And in the case of exothermic processes, solubility decreases with the increasing temperature. The dissolution of ammonium chloride, potassium chloride, etc. are coming under endothermic processes. While the exothermic processes such as the dissolution of sodium hydroxide, potassium hydroxide, then calcium hydroxide, these can be classified as exothermic processes. So the solubility of ammonium chloride, potassium chloride, etc. are increases with the increasing temperature. On the other hand, the solubility of sodium hydroxide, potassium hydroxide, calcium hydroxide, etc. decreases when temperature increases. So this is all about the Le Chatelier principle.